Alright, looks like I'm broadcasting to see if the microphone is correct and such. We're gonna wait. Yeah, for the other window to start playing. Waiting. There we go. See if the sound is sounding. It sounds like sound. We're gonna wait. Alright, it'll do. I could hear it anyway. Barely, but well enough, I think. Oh, that's right. Microphone's over here. That'll fix it. That'll fix it. All right, so we got the microphone right. I'm gonna try another camera trick. Try to use this, whatever it is, camera on a string. I tried to use webcams, old Microsoft webcams, and they wouldn't work on Windows 10. Windows 10 sucks. Anyway, yeah, I know this camera. Whatever, I like the effect for now, so we're going to use it for a video or two. But yeah, we'll get bored with it eventually. Move to something more reasonable. So I thought I would, I have to figure out the whole electron photon thing. And, there's different elements of how the energy is transferred, the momentum, the polarization, whatever you want to call it. We have to call it one or the other, apparently. Apparently I figured that much out. You have to call it one or the other. I wonder if I could hang this thing from up there. Let's see how that'll work. It might work. I don't know. Let's see, will it hang straight down? And let me look at the camera over here, see if it works. I'm trying to do a little technology. Okay, I'm experimenting. Yes, that's part of the reason why I did this also. Okay, the focus isn't great, and yeah, it's really delayed. That's not good. But what are you gonna do? I don't know if I can do much about the delay. Let's see. I'm gonna move it down, and then as I'm moving it down, it's delayed again. So it's got like a 20-second delay or something. I should put some writing in front of it, see if it picks up the writing. There's lots of drawings. That'll be a good test. Sorry, you don't need this part, but you're going to get it anyway. Bend this thing. Try and get it to hang straighter. That's part of the problem. It's hanging a little crooked. So it has a focal length of about, it's going to be more like 4 or 5 inches. And let's see how that goes. Yeah, it's funny. It's focusing that 10-inch thing way over there is in focus, so I guess it's higher than I thought. All right, let's go further away. I don't know how the focus can be this uneven. Very strange. Stuff going in sideways is in focus. Stuff straight up and down isn't. Explain that, please. All right, that's a little better. So yeah, it's really specific. All right, maybe I have to tape it to this thing, and then it'll hang straighter. I don't know. Sorry, this really isn't your problem. But there's nobody here right at the moment. Oh yes, but you might be viewing later. And I'll be doing all this unnecessary jabbering. All right, let me try it lower. Almost done testing. Almost done. Yeah, okay, it works low. So that's probably the way to go, is low rather than higher. So we just go lower and a little crooked, and so some of it will be out of focus and some of it in focus, maybe. I don't know. We'll find out. Turn that. Yeah, I don't know. I got to figure out some way to make a stand that maybe I can use this silly thing. I don't know if it goes up high enough, but we'll see. Oh. Of course, I haven't used it in so long I can't turn the frickin' screw on it, so I guess I can't use it because I can't turn the screw. Let's see. Yeah, I don't think. Well, it might make it almost. It'd be perfect if I could. Yeah, if I was a little clever, then this would work probably pretty well. If I go get a pair of pliers. But who wants to do that, right? Let's see. Yeah, that's probably got to go a little higher. There won't be enough in view. Wow, it's really delayed. Okay. And it's really out of focus. But maybe I won't care. Sounds like me not caring. Yeah, fucking thing. Oh, that's really stuck. We have tools here. Hey, there's another flashlight. What's it doing way back there? Huh. Yeah. These batteries charged. Okay. Alright, so I have found something anyway. So it's good to get some free stuff now and then. Ah, this looks like a pair of pliers. There, okay. Seems to be turning. Let's see if this thing moves. Yeah, it does. Doesn't move enough though. Sorry. Just, you know, scientist. You know, yeah, scientist at work. Ah, it has a thing to stop you from doing what I'm doing. So I guess I ought to say fuck you to that too. I don't know why it's trying to control what I'm doing. It just seems totally inappropriate. All right, now I can get rid of this cord over here or something. I think I can. I believe I can. All right, now we're almost in business now. Yeah, I can't see that, and the delay is still hideous, but I think that might work. All right, so get rid of this paper, and then we'll try to draw in the space provided, which I'll have to identify somehow. All right, I'm sorry, I'm still taking time to do this. Oh, Jesus, this delay is hideous. Hopefully when I start drawing it won't matter. Hopefully. So it's somewhere in this range. Yeah, just about the range. Okay. All right, I think we're ready to begin. All right, so now I have to put on the screen share, see if that'll work, and find the camera. We'll see what happens. Moving to this thing, and yeah, I really can't play both, so we'll just have to go with the one. All right, that appears to work. Doesn't look like it's going to be very good focus, but we'll see. All right, so the problem is that electrons. Okay. Yeah, I don't know. This sync is just so bad. And is it reversed? Oh, don't tell me it's reversed. It's reversing the image, you cunt. Yeah, that is weird. Okay, I get it. I can turn the camera. That's what we'll do. Okay, so I can rotate the camera one turn here. Maybe this way. I'll see how that is. Ah, interesting effect. Okay, now where's top and bottom? So this is the top, and this is the bottom. Down here, right? Yeah. So it's really so delayed. It's just really hideous. It's the bottom going down. Come on. Where's my finger? Going down. And now it's going down and it's still crooked. Ugh. All right, if I turn it this way, what does it do? Now it's probably even worse the wrong way. So I'll move my finger in the downward direction. Yeah, that's exactly wrong. So go this way. And my hand will be in the way when I'm drawing. All right, turn the camera. All right, this isn't working very well. Might have to give up and resign. The fact that it's just not gonna see a webcam would be much better, so I wouldn't have to worry about the focal length. All right, come on, up and down. I can almost see the lines in the paper. Okay, so that'll tell me something. Lines in the paper. All right, so that's exactly 90 degrees off. So if I turn it 90 degrees, that should be correct. Oops, too much. All right, go back a little bit now. It'll probably be upside down, so I'll probably have failed. So I count from the bottom here. Please. Oh, yes, so that's correct now. All right, so now we're in business. That didn't take forever. Almost, not forever. All right, so the problem is, all right, you have the two slit experiment. What I need is small pieces of paper. Probably should have cut some ahead of time because I have this on top of my paper, and that's not very good. I don't know if this little shitty notebook paper, what kind of back? Oh, it has a white back, so that'll work. I use these little pieces of shit. I never liked this little notebook anyway. All right. The delay is going to be a problem. All right, so anyway, we have the two slit experiment. And the idea is that there are electrons in between the slits and that they are accelerated. So let's just say that's an electron and it gets accelerated. And instead of moving straight, unless there's other electrons in a pattern that it can move straight, so let's just say there were a bunch of them in a row. It can't go straight because it hits the other electron, so to speak, the force. So the theory is it moves at an angle and that it releases the photon. Now, the thing is, the photon is actually made out of, so we'll do photons in green, is actually made out of 2 tons. So it has to release 1, and then it has to release a second one, and this distance has to be at the right wavelength. So my speculation is that what's really happening is if the electron is moving, it changes the frequency, and that's when it creates heat. So it creates infrared radiation. It degrades some visible light into infrared radiation if it's moving. And if the electron is stationary and then reverses direction, that's when it will release a photon of the proper frequency. All things being equal. So anyway, so the problem is a more detailed explanation of that phenomenon. So what I think I have argued reasonably is that this angle, which creates you end up with the pattern over here, that it is just about the fact that the electrons in different locations in the slit, so we have all these different locations that the photons come in, and at these different locations you'll have a different amount of deflection in terms of how much the electron won't be able to move this way, because the electrons are more tightly compacted because of the greater field energy. So I think another subject worth talking about, so let's move the page up a little bit, would be the nature of the forces pulling on them. So my argument is that there's, I guess we'll use, well, we could use another blue maybe. Maybe the two blues will show up. We'll see if they show up as a different color. So there's a proton, inside of the atoms. And then there's the electrons. We'll use the green for the electrons. That'll be safer. And then we'll use the dark blue to illustrate the free electron out here. So this is in the atoms, has these electrons are in positions, let's argue, that are rather rigid. And so you end up with one of these circumstances where you have like a -1 force here, and because of the other neutrons in the nucleus, you have like a +4 force in here. So I guess I should have done +4 in a different color in terms of charge. And so what happens is from a distance, from far away, that entire force looks like a +3 charge. But as you get closer, this +1 gets stronger and stronger. So this repelling force overwhelms the attractive force. And so there's a balance reached between the electrons. They have to negotiate a balanced distance from each other and distance from the proton. And that's what sort of happens in these field lines. So the argument would be the field lines that are inside this gap over here, in this slit experiment, in the narrow field lines, the ones close to the surface, those field lines, the electrons are closer together than the field lines further away. The electrons, because there's less force pulling, there's less force capable of overcoming the negative forces the electrons have towards each other, so they spread out more. And so it's the more spread out they are, the straighter they travel. The more compressed they are, the less likely they are to travel straight. They're going to do this bending thing. All right, so that would indicate that the closer you are to the surface, the more likely you are to get bent. The further away you are, the less likely. And that the bend would be by these rules of distance. So the distance, the dark spaces, okay, so if you could call that a dark space. So this would be the light band, the blue, and then you have the dark space in between, which I'm not illustrating very well because it's not even in the camera. Yeah, where the hell is the camera? Oh yeah, it hasn't even moved up to this yet. Well, how did it do that? That is really strange. Anyway, I mean, I guess it's skipping parts, besides missing them. So here's my pen again. Anyway, so this is the dark and light band. So the green, let's say, is the dark. The dark is actually this space in between the field lines where there's no electrons. So those are the dark bands. Where the electrons are is the light bands. So that's the on-off pattern, is the electrons as they line up. All right, so I think that's reasonable. That should be acceptable to those who are following along. So again, the argument is that between the slits, do this again, and this goes for double slit and single slit. But obviously, as you vary the distance of this impediment in the middle, you change the lines that it's going to produce. So the idea is that there are lines of force in between these two slits, and that not a very good way to draw it, but anyway, and that the ones further out, the electrons are further apart, and the ones that are closer to the surface, the electrons are closer to each other. And the space between is the light goes straight through and goes to the target, and that's why in the single slit the central maxima is larger and, 8 times brighter, or 9 times even, than the next slit. Is because obviously in the single slit, a lot of light goes through the middle, where in the double slit, obviously it doesn't go through the middle. And another question would be, what happens to this energy? So this is another part of it. All the light that hits these surfaces, that energy has to go somewhere also. But from the experiment of the random photon, like the single photon experiment, which again hasn't been duplicated enough times, where, that's another thing of, for physics to bend, to use this stuff as the entire foundation for physics, this experiment, they really should have picked at it a lot harder. To think that, there's been very few duplications of the idea of sending single photons, by creating a highly opaque, but not totally opaque blockage to the source of photons, and then just letting it sit for a month and see how many photons end up on a photographic film. Seems they could have done that by now a few hundred times and tried different ways of doing it. But anyway, the idea of the energy in the surface being connected to what happens to these photons going through, you can probably eliminate as a reasonable explanation for any wave function, just because if the photons are only hitting here once a day or every 6 hours or something, there's little likelihood that any energy that goes in is going to be dampened. But anyway, I'm getting really, really into the minutia with that. Sorry, vegetable juice. Probably could use a little bit of cigarette also. So have a little of that to go. So yeah. I don't know if you can focus this camera. I don't think so. No. Yeah, maybe I'll put a lens on it that I can focus, and that'll make it a little better. It is irritating. I have 3 older webcams. Not one of them would work on Windows 10. Well, one of them isn't even that old. It's one of those Chinese ones. And, it works on my XP machine, but it doesn't work on Windows 10. Piece of shit. Anyway. So, yeah, I do have to... It's very hard to talk about the 2-slit experiment without getting into this deep argument about this transfer of momentum through these electrons, because that's really the cause of the thing. And you can just say that. I think it's a valid argument to say that we know there's field electrons around surfaces. It would be logical to think that the photons are hitting the electrons, and that the electrons are deflecting the photons, diffracting. And that's the explanation for the patterns. And it's almost like, well, what's the counter argument to that being a viable theory? I don't think there can be a counter argument to that being a viable theory. Just as a simple theory, as a statement saying it's just as good as, it's at least as good as, let me put it this way, the photons split in half and go through both slits and create a wave interference pattern and then turn back into a single photon. That explanation versus no, they just deflect at a different rate depending on how close they are to a surface. So the closer they go to a surface when they enter the 2-slit area, the more likely they are to be diffracted. And if they don't hit an electron, they don't get diffracted. So they only get diffracted based on the positions of the electrons, and the electrons are automatically going to arrange themselves because of their dislike for each other in a proportionally distance from each other based on the strength of the field. in the area in which they are composed or placed. So the closer they are to the surface, the closer they are to the protons. The closer they are, the more force they're going to feel, attractive force. All right, so now the discussion of the exact mechanism of the creation of the new photon. All right, so the idea is you have an electron and a photon's going to hit it. So again, we'll use photons will be green. All right, so, and we'll do the photon, well, just as Feynman does, we'll use the squiggly thing. I don't know if that's a good idea, though, because we're yeah, now it's a sperm. Anyway, but the idea is that once the photon hits the electron is going to try to move forward. That's the direction of the polarized energy is in this direction. So I have to try to find some way to say, see, in reality, I'll do a in reality drawing maybe. Yeah, so we'll do an in reality one first. In reality, everything goes in straight lines and nothing ever changes direction. So in the 3 dimensions, there's just stuff going. And so all these are just loaded with little arrows, all just going and going. So it's all this stuff. And the only thing that constitutes matter is the polarization, so that there'll be a place here where polarization is all the same. And that polarization will, even though the momentum will go through and leave, the polarization won't. And the polarization will reverse direction, will reflect. And so it will be caught in a pattern of going and then reflecting and going and reflecting and going. And so it's really just going back and forth. And that constitutes, when you put that in a lot of different directions, that would constitute an electron. So it's all the same polarization, and the momentum goes straight through. So you can always follow the equal but opposite momentum, in the sense that you can follow that there'll be a conversion. A force will continue out. It's just that it won't be polarized, this polarization, and that and then if this thing does change, it's going to change because the right polarization comes in. So if polarization enters, then polarization will move this forward, in the sense that you'll have extra polarization goes in and extra polarization comes out. This circle will end up changing its position, in a sense, and that's what we consider the movement. But it's actually, so it actually will move the speed of light for a brief second, and then this rebound will happen, and in that rebounding process there'll be lots of conversions of the stuff going in these other directions, and so that polarization will also be moved forward through those interactions, because now the timing cycle, the amount of time it takes to get from here to here, is a lot longer than the distance from here to here. You can sort of see that. So the length of time it took to go one way is going to be different than the length of time to go back, and that difference in time is going to be critical to things like the frequency of this polarization when it leaves. And that makes the difference between maintaining something's frequency and increasing its frequency. All right, so I think that's a useful enough explanation. All right, so back to the little sperm. I don't know what I just broke, but I won't worry about it because we're busy doing science. So if somebody wants to argue this, conventional physics and be in the room, just comment and ask for the link and such. Yeah, not too many people watching tonight. Well, the time change probably throws off all the Americans. Are all, and then Trump getting elected. That'll. Anybody with a brain has got to be in a little bit of trouble today. Yep. Very sad. Pitiful times in America and such. All right, so anyway, so the photon comes in, hits the electron. So as stated, this electron, let's just say there's like I said, there's another electron here, and the field tendency is in this direction, right? So because we have that +3 thing, we have the stronger proton with a weak electrons preventing things from going this way, but the tendency is to want to go that way. So this electron, instead of going forward, is forced to evade the field and go in some other direction, probably in a parabola, but we won't worry about that in this argument. So it's moving in a new position, but there's other electrons in the way, so it really can't go to any of these positions. All of them are blocked by other electrons. So there's no position that's going to be comfortable except going, frankly, the way it doesn't want to go, which is away from the proton. So the only way that would have created enough room for it to expand would be to have gone opposite to the more congested force. So it's heading for congestion, more electrons, and that's just not going to work. So this is basically the scenario where they talk in physics of the energy level of the electron, and so where they call it the when they say an electron jumps from one orbit to another orbit, it's really not jumping from an orbit, it's changing its acceleration. And when the electron absorbs the photon and that it's able to keep it, then it means that it was able to move to a new position. And then the other electron moved, and the other electron moved, and the other. So if it can take somebody else's position, that would be what they consider an absorption of a photon, because now what happens is some other electron moves to another location, and it pushes the other electron out of its location, and pushes the other electron out of its position, and that's essentially electricity. So it converted the photon into an electrical current. So that's that's what happens typically in conductors. Okay, but we're not in a conductor now, we're in the field outside. We're in a free electron environment, and free electrons aren't going to be as easily pushed because they're going to be able to jiggle around a little bit, and so they'll push back essentially. So it's going to be less likely to be able to push another electron and create an electric current. And so what it's going to end up doing is accelerating, pushing everybody a little bit, making everybody a little bit uncomfortable, but everybody's going to run back to their spot, and this is going to have to go back. And so I guess what I would argue is happening is, okay, so now we have to understand the idea that the photon is made of 2 tons. So I have to represent that in some way. So you have one that goes in, and then there's going to be a second one at a frequency, at a timing cycle. And the idea is somehow the same photon gets released, the same frequency. So when they go in, as I sort of stated, what really is going to happen is there's going to be the first one goes in. I'll try to draw the electron below this, so the idea is that these two are going to hit this thing in this way, coming from this direction. Okay, let the image catch up, and so so the first one comes in and it moves some bend, and then the second one hits it and it moves further, and so it's additive in terms of the amount of bend. Now I didn't show a lot of bend there, just as it isn't much bend, because again the field is down in this case. You're down. Yeah, which is probably my down also, hopefully. But those are the two hits that take place, and depending how quickly those two hits happen will change how much the deflection is. So as I stated in the video when I explained this stuff, let's find a little empty space over here. The arc of how much deflection there is will be decided by how quickly you're hit the second time. So the sooner you hit the second time, the less chance you'll have to drift in. So you'll have a straighter course, and the slower, the more time you'll have to drift, and so the more bent you'll be. So the slower electrons bend more, and the higher frequency bends less, the lower frequency bends more. So the higher the wavelength anyway. So the red light bends more, the blue light bends less because of the speed of which it's hit, which means there's less movement in that direction and more movement in this direction over a period of time. And that's all that really matters. But anyway. All right, so back to the bend. And this piece of paper is too long. Just try to fix that. Anyway, okay, so all right, so we have it get hit twice. It's going to bend, and then it has to re-release the same photon. Right, that went in. And my argument is that re-releasing will basically be, say this electron is there, and I'm just drawing it out of place, is now going to return to where it was. So it's just basically a kind of a reflection or a rebound, and then to do that, it needs acceleration in that direction. An acceleration in that direction will mean that something has to go in this direction, and that'll be the photon being released. And the photon is going to be released in the polarization that is the same as the electron. So the electron is basically going to just sacrifice this forward motion. Okay, so the photon had to be the same polarization as the electron in the first place. So that's a key thing here. So they should be the same color in a sense, just because I've been using color to represent polarization. But the fact is the photon is polarized quanta at a frequency. I would argue that there's still other green ones in here. Okay, like a photon would have greens mixed in, but the blue ones are at the key frequency. At this frequency, they're always blue, and that would indicate a photon. I mean, that's a very important point to make. The greens just go through the electron, though, so that's the point to remember, is the greens are irrelevant to the status of the electron in terms of it won't interact with the blue crap. It won't gain acceleration as a consequence of interaction. The argument I made before, it's the X argument, that there's no difference if the polarization doesn't change. There's no way to tell the difference between the two worlds, and it's only when the polarization is changed that you can see the difference between the two outcomes. So anyway, so
So with reflections, it's kind of just this kind of thing, two greens, and then the blue reflects. So it's a maybe this pattern. Yeah. So the green goes in, green comes out, blue goes in, blue goes out, and nothing really changes in a sense. Anyway. All right, back to this. So for the electron to go back, it has to give back this forward energy. So it had this reason to go forward, and now it can't do that. So it's going to eject it. And so the first one it would eject as it's still moving this way, I would presume. So it still has a little bit of motion going forward, and it ejects the first piece of the photon, and then it's going to and then when it changes, so it never comes to a complete stop. So what it essentially does is it loses half of its momentum, and then it doesn't just lose the other half, it gains momentum going back. So there has to be a conservation. It has to go back at the same speed that it left with. Well, it doesn't have to. But that's what you're converting. So you're releasing the original photon. That would be conservational. And the energy pushing it back is actually the field energy of the other electrons. So that's the key ingredient here. These other electrons are the ones that were compressed and changed, and now they're the ones that are going to push that back. So the real thing is just the release. So it is just the stopping. So slowing down to stop, because the force is pushing it. So there's extra force coming off the other electrons. You can't really see any of that in this drawing. Yeah, just no way. New piece of paper, maybe? Yeah, we'll try one more. One more piece left. All right, so let's see how to draw it. So what we have is an electron that is plus 2 tons. So we could say this is the electron, and it's plus 2 tons in, let's just make the direction in some kind of way like that. So it's got plus 2 going this way, and now it has to release those 2 at the right frequency, the same frequency that they came in at. And so the force comes in from the other electron saying you can't go here. That force is going to stop this electron by giving it force in this direction. So these field electrons are admitting potential acceleration. That's what they're admitting. So all the electrons are all exuding push away force when stimulated. So whenever you accelerate an electron, it gives out this blue stuff, and the blue stuff makes an electron go in the direction of the blue stuff. So whenever blue stuff hits the electron, it goes in the direction of the blue stuff. So whenever it has extra blue stuff on one side, it'll go in the direction of the extra blue stuff. So it got hit by extra blue stuff, which was the photon. So now it's going in this direction. By going in this direction, it's pushing other electrons, which are expelling blue stuff because they got accelerated. And the expulsion of that blue stuff hits this electron, which says, I'm going back this way. But to do that, it has to give up the blue stuff it took in here. So this blue stuff has to come out here. And I guess I would argue, okay, that so the first one gets released, and without, I guess the argument would be without the pair. Let me think. I'm just trying to think if you can have a half bit. Whether there's some obligation to always add these in twos to be able to maintain it in terms of, as I stated before, the electron is basically made out of quanta, tons, moving one way and then hitting the external force, and then they just reverse on each other. So this blue one turns around, it hits another blue one, they both turn around, so that means this blue one goes back this way, it ends up hitting another green to go back this way, so it ends up reversing again. Okay, so this is the part that gets really gnarly. And this one, in this interaction, this one turned this way, and now it hits this one head on, and that head on collision makes this one go that way, and it makes this one go this way, and then this one will go through until it hits a green that's coming here, so it's going to end up hitting a green a little further out, but it's still going to hit the green, and so then it's going to reflect back this way. So, but it all adds up to the fact that, it does take some, you do have to go through these reflections before you get something that goes far enough out. So that's how it escapes, is that it gets separated enough from what you call the shape of the electron, which is always bending and moving and twisting. And once it gets far enough out, then it's gone. Now it's free again. And now if you have two of those at the right frequency, then you have the photon. Photon. Yeah. All right. So yeah, that still doesn't really explain how the frequency is maintained, but I guess I would argue that the frequency is locked in the same way it got absorbed. So when they came in, it was like this arrow was the first piece that went in, and then a while later through this process the second one came in, and so you could say that maybe this is the first arrow. It's way further into this reflecting back and forth process. So the two have a distinct different distance, and just as they went in based on a timed reaction, they're going to go out based on that same timed reaction, because it's at that timed reaction that you're going to get this distance far enough out where you escape the electron, and the electron starts moving in the away direction. So it's basically the electron, the pattern that is the electron, like a bunch of dots. And it's really just about when a dot gets too far out, it's no longer part of the school. Oh, I have to move that out. So if you had a bunch of dots, it's just about when one gets too far out, then it's not part of the clump again anymore. So, dots go in and become part of the clump, dots go out. So when they come in, they move the clump in the direction that their momentum is in. The first movement is in the movement that they're coming from. So before an electron moves, it actually jerks backwards. Okay. And then, so here's its original position. Its original position would be this green circle. And then its new position after the jerk backwards, it's going to have more arrows going this way. So the new line is going to end up being here. So the new electron is going to move forward, and that's how it continues its progress. So its progress is essentially, it goes a little bit more forward, then it goes back, a little more forward, and it goes back, a little more forward, and it goes back. And so that's how it makes forward progress, is just going a little bit more forward than it goes back. All right. So we do have some comments. And so we'll read them. But same guy keeps talking over and over and over. They claim they accounted for errors and it still works flawlessly. They claim they accounted for errors and it still works flawlessly. I have to go back. I guess he's got some statement before that. What do you think about the newer, unreviewed, but direct source from NASA and EM Drive? I don't even know what that means, so I don't think anything about it. What do you think about the new unreviewed but direct source from NASA REM drive? What does that mean? They claim they accounted for errors and it still works flawlessly. I don't know, EM drive, I don't know what that is. Somehow electrons or photons are thought to somehow be involved in making some motion that obeys the equal action-reaction mechanics of Newton. Well, that's exactly right. That's what quanta is. That's what conservation implies. So I don't know if if NASA just figured that out, they're pretty stupid, because I think Einstein could have explained conservation rules. That's what E equals mc squared means. Look it up, though. No, I don't really feel like it, shithead. It's interesting because they say in physics, they say the physics in it shouldn't work based on the physics, but it ends up working. Yeah, well, I'm really not going to waste a whole bunch of time on, I could sit there and explain, they think, okay, that there's wormholes inside of atoms and somehow electrons go faster than the speed of light through the electron. I mean, they think all kinds of, well, they say it, and it's obviously stupidly said, because they don't, what they really mean is the electrons move faster than the slowed down photons. Like, say if glass slows down photons by 40%, they argue the electrons are going faster than the slowed down photons, which means they're still going slower than the speed of light in a vacuum, but they're going faster than the photons are in the medium. And of course, that's possible. But, I mean, you ask a stupid question, then you can get a stupid answer. Anyway. Look up leaked NASA paper shows the impossible. No, I'm not going to bother looking. I have an agenda here that doesn't have anything to do with your agenda. EM drive really does work. Well, whatever. I guess you're saying they have a drive for a spaceship or something, and that's all these assholes. They want to keep trying to invent perpetual energy, and it doesn't really matter anyway, because even if you found a drive for a spaceship that didn't require dragging external fuel, it doesn't matter. You got nowhere to go. You can't really go as fast as they want to, because you're going to plow into all kinds of matter that's going to be going a lot faster because you're going faster, so to speak. So anyway, is the paper. Yeah, well, I'm just really, I'm really not that fascinated. I'm here to debunk the foundations of quantum mechanics and to explain a unification theory. I'm not here to waste my time pointing out how NASA can't, figure out that there's an explanation for XYZ. Anyway. Hello guys, I'm a prankster. I need your help. Well, a pranker. Well, whatever. Goodbye. I don't need to read any further than that, do I? No, I don't. So anyway, yeah. Hello guys. For that alone, blocking seems quite appropriate. All right, so yeah, so the only way I can really explain why the frequency stays the same is to explain all of these interactions. And in here, that's no point in trying to do that in this video. But as stated, what happens is if the electron has actually got momentum in a direction when the photon enters, then the photon will leave at a different frequency. So for a photon to hit an electron and leave at the same frequency when the electron changes direction, the electron had to be at a it had to have no velocity. And if it does have velocity and the photon hits it, then it's going to convert the photon, likely going to convert the photon into infrared radiation, which is heat. So that's why in most cases, when photons hit electrons, or when photons hit matter, they end up being converted into heat because the electrons they hit are moving. So that would be my explanation for that. And they're moving perhaps in the direction opposite to the movement of the photon. If they're moving in the same direction, you might speculate that it would be converted into ultraviolet radiation, but that the ultraviolet can't go anywhere in matter because it's going to hit another electron and be converted probably into infrared. So I have to think on that one. There's also the possibility of the tangential interaction. See, that's what happens here. When these are going back and forth, at the same time, they're interacting with all the tons going in the other two dimensions. So the tons going in the other two dimensions are interacting with these. They're going back and forth this way. The ones going back and forth this way and this way, in and out, are all interacting with these. And that's how they end up converting this motion in one direction into the updating of all the other. They have to update somehow. The other two dimensions have to get forwarded in the same direction. So it's the let's see, a good way to draw it. So this something's moving in, say, this direction. It has to update the stuff moving in these other two dimensions so that this stuff moves in that direction. I don't know if that's in the camera, but we'll find out, I guess. Go back to the camera view. Yeah, close enough. So that's happening through the process of those interactions, is that the stuff moving in these dimensions is being updated to this with this motion. So it's a little bit of this energy is being used to push all of these things a little bit in this direction. And that accounts for the electron's overall movement being much slower than the speed of light. So a tiny fraction of the speed of light. When small interactions. Obviously, you can get electrons to move pretty quickly if you hit them with enough energy. I mean, if enough stuff's coming in, it's going to get everything pushed rather rapidly. But electrons want to stop. So I don't think you can. I think if you shot an electron into space, I don't think it would keep moving. Yeah, I think it would find a. I think it's not matter, and so it doesn't have enough of a mechanism for maintaining a velocity, and that's why it only moves across charges. So unless you create you have to get an electron to move, you really do have to have a plus and minus charge. You have to shoot it from a low charged area to a high charged area. I mean, a more negative potential. So this is like sort of opposite, because then the signs are opposite. So it's always a mistake to write it this way because it has to go to actually a lower amount of electrons, which the positive means. So, but that's what you always have to do. You always have to You have to shoot an electron by giving it the impression that it's going from a crowded spot to an empty spot, essentially. Yeah. Yeah. Yeah, so you have to create the crowded spot to be able to shoot it. So if you just place an electron, you just let one go in space, there won't be any crowdedness to push it. So you have to push it to get it to go into the space. You have to create the pressure. And I'm just not sure you can maintain a velocity, because the inverse square law will kill the pressure. And so it's essentially the gravity will stop, and therefore I think its acceleration will stop. It only accelerates while it's being accelerated. Only accelerated while it's being accelerated. It only has velocity through acceleration. So it only has acceleration, no velocity. I'll have to remember that, because that might be a viable theory. And such. So, let's see, is there anything else I need to cover? Yeah, that's mostly what I was working on. So this seems very viable. So I think this will work. So I think I have to work on my computer program, because now I pretty got the motion down. It's just this complex reflection thing that takes place. Yeah. And the rest of there is no conversions. Blue has to go in for blue to come out. And yeah, so polarization is never additive. You're never creating it. You're just always converting it. And you can look at it either way. Either follow the momentum and just pay attention to momentum, or you follow the polarization and only pay attention to the polarization. But you can't look at both, because if you look at both, then you break conservation in terms of even your perception. Yeah, I think that's correct. Anything else I have to add? Let's see. No other comments. I guess I can turn the screen share off. So I guess I'm done drawing. So I guess I can turn it off a while ago. But anyway, see how that worked out. And such. Yeah, really, that delay is irritating. I mean, it's even more delayed from your world. Ooh. How do I get rid of the white balance right here? Boy, it really got thrown off. Let's see if I turn the light off. Ooh. Oh, I didn't even, that's really, how do I fix white balance? Just had to put a white piece of paper, maybe. Maybe that'll work, Gary. Okay. Still didn't quite do it. I guess it's picking up the non-white on the paper. Yeah, surprising that it doesn't rebound. Try black balance. Yeah, that's a good idea. Find something black. Not black enough. There's blacker and blacker and blackest. Okay. Now see what happens. Nope. It's interesting. So it didn't survive. Camera settings are not. Yeah, they don't rebalance. Great. I guess I could just turn this light off, and that helps a little. Because, I don't want to fiddle with the camera settings. Maybe if I get out of the picture. Nope, that didn't fix it either. Maybe if I shine a flashlight at it. That's an idea. Yeah. Maybe that worked. Let me try it with the light on. Nope. Yeah, you really can't fix it. It's broken. Right, let me turn the other camera off. I hate to turn it off now that I've got it there to play with. All right, leave it for a minute. Yeah, no. All right, wasting your time. Turn the light off, and it's just not going to work. All right, well, so much for the camera settings. Yeah, now the hand thing works for the it works for the focus, but it won't fix the white balance, the gain. I guess I could try turning the camera off. Yeah, that might work. And then turn it back on. Yeah, that's a good idea. Camera off. Camera on. Ooh, I'm reversed. What the fuck happened? That's totally fucked up. Turned on. Camera is off. Well, it says it's off. Well, okay, now it looks like it's off because the icon is showing. All right, camera back on. Yeah, so I never knew that. It'll reverse the camera image as you turn it on and off. So this should reverse the image. Yep, that is fucked up. All right, well, that's something new I learned. So your left can be the right. Just turn the camera on and off, and it switches each time you turn it on and off. Pretty cool. But didn't fix the white balance problem. So, fuck it. Yeah, that's what I thought to say. Fuck it. Can't really turn these lights off without getting up, and I don't want to get up for reasons that shall remain my own. I.e., I am not wearing pants. I could just fold something and put it over the camera, I suppose. But yeah, that's funny. I mean, how much, it's pretty dark here now. So it is kind of funny that it still works in pretty dark conditions. Turn this camera light. See, all these different lights are on. See which ones change anything. I don't think that changed anything. Not really. Not that this isn't a bad look. I kind of like it. A little bit scary and such, but you can see a lot more of the room. But it is really low light. I'm just surprised that it's so freaking overgained. No. Yeah, I really should readjust, but I have to open and close the room, I guess, or maybe, well, if I turn my camera. So let's do settings. Okay, I'll play a little bit. So if I change my camera to the other camera, and then that should really fuck it up royally. And we'll see how that works. I don't even know if it's going to display the other camera directly. What we'll find. Oh, well, no, it's already being used by the other. Well, let me close the other window, and maybe it can grab the camera image. All right, well, I'll hit save, and we'll see what it does. It said, fuck you. Yeah, I ain't doing that. Yeah, I mean, I needed to close it, I think, beforehand. But anyway, at least now we'll be able to see if the other camera loads fresh. Yeah, it's not previewing. So I don't think it likes me fucking around. Switching the camera. No, it does not. Alright, so that didn't work. It appears that it didn't work anyway. Let me try one more time. Logitech camera, come on, you can find it. Look for it. Come on. You know you can do it. You know you want to. Let me just switch it. I won't even switch to the other camera. Just keeps trying to switch back. Saying, fuck you. Nope, not doing that. Alright, now it's broken. Very good. I learned how to break it. Good job, Gary. Alright, well anyway, I didn't want to stay in too long anyway. Just trying to recover from the whole depressing thing. And I mean, I got so much to do and I just feel so undermotivated. Everything's just so horrible. Awful, horrible world. Yeah, but I'm not dissatisfied with this. And there was way too much, for some people probably, but I mean, I really do have this nailed. And, I just need somebody who's really understands what I'm talking about to say, I get what you're saying. Yep, that answers all the questions. Yep, very good. So anyway, we'll call this a broadcast and move on to the next piece of shit. Oh, Piro's made a video apparently. President Trump, sound at 640. He still can't get this video thing figured out. It's just so funny. I mean, yeah, I know I just blew up my camera and all that kind of shit. I wonder if I can do screen sharing still. I mean, now that it doesn't matter if I don't have any sync. Let's see, what do we open? I guess we'll open this and see how that works out. All right, so that's the video. Okay, yeah, so what I'm seeing is Piro's got a little link here. So maybe I'll open that. If I open it in this window, I lose my chat, so I can't do that. Let's see if it opens the new tab. It looks like it is. Okay, that worked. So, no sound. Way to go. You're doing well there, Piro. So you have to go to 6 minutes or something. And what's he going to say anyway? It doesn't have anything to do with stupid immigration. Yeah, it does, asshole. That's all it was about. If Hillary Clinton just would have changed her rhetoric a little bit and just said something like, yeah, I feel your pain. It's really hard doing this whole world economy thing and migrating and blah, 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 and blah. I could see it, but now 20 comments. Who the hell's commenting? Let's see. The country has gone to heck. Oh, he has a good attitude. Oh, so he's all ready to play along with Trump. Stupid cunt. Anyway, since I'm here, I'm just going to do a little bit of this. Piro's such an asshole. And a douche. Okay, still no sound. Gotta go a little further. Yeah, he's looking. Where's my sound? Oh, there it is. I found it. I'm a computer expert.
I guess what I'm supposed to say on that shit again.
I guess so.
Well, I was just saying it's democracy.
No.
I was saying I hope that
it really
Trump
isn't.
succeeds. I'm going to look especially.
It isn't democracy. So right there, I mean, democracy is one man, one vote. That's not what took place. And clearly, there's nothing democratic in the fact that, well, no, I mean, it's democratic in the sense that at least this wasn't a congressional election. But go ahead.
For issues where I agree, right? Like, okay, yeah, renegotiate, by all means, renegotiate.
He can't renegotiate any of those trade agreements. There's nothing to negotiate. You're either going to be isolationist or not. So what do you think What do you think the Trump compromise with your silly open border shit is? There is no Trump compromise. Well, no, there's just no point. It's pathetic. There's nothing. There's not a single Trump policy that's rational. He doesn't have a rational solution to a single problem. There's no compromise with irrational nonsense. He's going to put a lunatics on the Supreme Court. Then economically, he's going to do exactly what we don't need. Capital has no value. That's why interest rates are so low. Capital is absolutely useless. And now he's going to give the richest people in the world more capital to play with. What's the point? And if he cuts just business taxes, that's fine. I mean, no, I wouldn't offend. It doesn't offend me because that's not money going to rich people. Because the consumers can gain from that also. But obviously, when corporations are international corporations, it's not likely to be us that will benefit from it. But the point is there's no way to finance it. It's not about the fact that you're giving away tax cuts. It's about the fact that you're not paying bills. So when you cut revenues coming into the government, that creates more debt. And the last thing we should be doing is making more debt. So anyway, there's nothing. Trump is an idiot. You're an idiot. You're on the opposite idiot sides maybe on some stuff, but you're both idiots. And idiots aren't what the world needs. So anyway, so irritating. Oh, Holiday made a video. It's winter and he's wearing his freaking wife beater. Well, let's go to the Holiday video because might be worth a laugh of some kind. Oh yeah, no volume. Not even close to enough volume.
I have an idea.
Got the speakers all the way up.
An idea struck upon me to make the juxtaposition, or to suggest the juxtaposition of two scenarios. One, consider the molecular machine, the biological molecular machine that is a sentient organism.
Oh, idiots commenting.
That, from a certain point of view, you could take the view that it had invented a mechanism of pain with the purpose of providing motivations to procreate and to safeguard itself.
Yeah, well, look, you're still not getting it. The purpose isn't any of those direct purposes. The purpose is to make value, okay, real. That's the problem of creating any machine. How do you make value real? And the only way you can do that, that's imaginable, is to create some kind of mechanism that somehow creates the concept of ouch. You make a whip and then you don't use it.
In its ongoing struggle to procreate. It's position number one.
Whatever. So what's position number two? I will pretend that I didn't just state that the sensations happen.
Position number two. Consider the molecular machine of DNA. You can also similar kind of take the teleological view that it too is imbued with a kind of purpose, that it has the purpose of replicating itself, that it has come together.
Right, and whether that purpose has any value is completely something that can be judged rationally and through some sort of equation where you establish some sort of math, okay? Some sort of math of how you apportion value to this idea of procreation. And obviously it has no value except that it makes some people feel good. But it doesn't have any intrinsic or fundamental rational value, as can be pointed out with the simple argument that obviously there is no negative effect. There is no horror because Martians don't exist. It's not a bad thing that they're not here, therefore it can't be made into a good to have them.
I could ask you to analyze why is this teleological way of thinking about the purpose of constructing the pain, the purpose of constructing
Again, it has nothing to do with the agenda of evolution. It has to do with what is the thing in and of itself. And you keep missing that point. If I put pain in a jar and shoot it into space, independent of its creator, the earth, independent of all other circumstances, it is in and of itself torture in a jar in space. It is bad in a jar in space. It should be shot down. It should be assassinated. It should be murdered. It should be crushed. It should be changed into some other arrangement, because that's a bad arrangement of matter. That's the ultimate big picture truth here. Anyway. All right, enough philosophy. Stop screen sharing. Hey, I stopped screen sharing and it's still screen sharing. That's interesting. Sort of. Kind of. I wonder if my camera will work now. Let's see. Try the settings. Put the camera on. Let's see if it works. Nope. Oh, that's really weird. So, I wonder if the, let's see if I hit DraftScience. Yeah, what the hell? No, it didn't switch. Okay, so it just stuck with the Holiday image for some reason. No, I won't worry about that. All right, anyway, I think we're done. I think I've accomplished my task, which was something like do this video thing. So yeah, I think I did that. I think I also killed my room link, right? Yeah, I believe I did. Let's see, that link ain't gonna help you any. Yeah, I guess I did. I guess I would have to go back. No, it's just Puro. I don't know where it is. I guess this is it here. Oh yeah, there it is. Okay. Anyway, Puro is so cute. Yeah, well, I guess that's a subjective kind of thing. Yeah, so I'm not seeing it. But anyway, till next time and such. I think I'm done. I think I'm worn out my welcome and whatnot. And so yeah, till the next time and such, and so forth and whatnot. Yeah.